Hello viewers, welcome back to my channel. So this session is all about the different allocation methods used in order to move the processes from the secondary memory to the main memory. So we call that under the heading called as memory allocation methods. Memory allocation methods can be of two types. One is the contiguous and another is non-contiguous. And further, contiguous memory allocation can be of two categories: fixed size partitioning and variable size partitioning. And the non-contiguous can be once again having two different categories. Paging is one, the other one is segmentation. So all these topics I'll be dealing in my future sessions, but presently I just wanted to tell you about the contiguous and non-contiguous. Okay, first let me tell about the contiguous in this session, and mainly I wanted to tell you the difference between the fixed size partitioning and the variable size partitioning. So to understand this concept, let me give one example. Always the processes are present in what? Present in the secondary memory. This is what we know, that whatever processes, whatever programs the user types, all those processes are present in the all those programs or processes are present in the secondary memory. But CPU is having what? Access to main memory only, not to the secondary memory. So the processes have to be moved to the main memory. Now one method wherein you can move the processes to the main memory is, first type is contiguous. That means all the processes will be moved in a contiguous fashion. But once again, in contiguous you have to see what? The fixed size and variable size. Contiguous is completely moving a process, the completely allocating memory to the process. Suppose if P1, P2, P3 are the different processes that are there in the secondary memory. Okay, when you try to allocate a particular memory space for a process, complete, okay, whatever number of locations that P1 wants, the complete locations are allocated to the main memory. So we say it is in contiguous manner, and that's why the name is given as contiguous memory allocation. So when you try to accommodate the entire process in the main memory, it becomes contiguous. You are not trying to take what? Partially the number of instructions from a process and place it. Rather, you are moving the complete process here into the main memory. You are allocating space in the main memory for the process P1, for the complete space that is required for the process P1. That becomes contiguous. And here we have two different methods in contiguous: fixed size and the variable size. So what is the difference between the fixed size and variable size? In the fixed size partitioning, so let me first tell you about the fixed size. The main memory or the physical memory is divided into, okay, partitions of fixed size. Let us assume this first partition is of 300 KB, just assume it. The second partition is of 150 KB, the third partition is of 200 KB, and the fourth partition is of 100 KB. Okay, this way you can assume. Now suppose if a process P1 comes here into the main memory, the process P1 size is 250 KB. Fine, the process P1 size is how much? 250. So P1 gets the space here in the main memory, but partition size is how much? 300. P1 size is how much? 250. That means this particular extra space, that is the leftover space, is there in this physical memory. So let me just mark it with a red color ink here. So this space is what? The 50 KB is not used here. 50 KB is the leftover space in the partition. And this way, if you try to move the processes into the main memory, let us take P2. P2 is having a size, let us assume, as 120 KB. Okay, when P2 comes over here, out of 150, P2 is making use of only 120. So another 30 will be what? The leftover space here. Whatever I am marking it with red ink is the leftover space. P5 is moved to the main memory. P5 is appearing here in the main memory. Let us assume P5 size is 180 KB, but when it is moved to the main memory, the partition size is 200 KB. So another how much? 20 KB will be left over here. So this here you are getting 20 KB, and in the previous partition how much you got? 30 KB. Okay, and let us assume that another process P4 also is moved to the main memory, and P4 size is, let us assume, 80 KB. Then when P4 is allocated here, there is a leftover space of how much? 20 KB. So this 20 kb is leftover space in the last partition. Here you have 20, here you have 30, and here you have 50. So this is called as internal fragmentation. Look at the definition, or what exactly you mean by internal fragmentation. In simpler words, memory that is internal to a partition but is not being used. So this is internal to this partition. The first partition ends here, the second partition ends here, the third partition ends here, fourth part. So this is internal to this is internal to this all put together you can see here this much is the internal fragmentation if you are considering this particular memory situation, okay, wherein we are trying to place processes P1, P2, P5 and P4, 4 processes. So only in this situation you can say yes, internal fragmentation exists here, and the value for internal fragmentation is 50 plus 30, 80 plus 20 plus 20. 120 kb. Internal fragmentation value is 120 kb. This is how you can say. So this contiguous method of allocation always gives this kind of problem. We call it as internal fragmentation. So this space will not be used for other processes as well. So that is why it is simply a waste here, everywhere as and when. So it is sometimes it happens that the process size may be equal to the size of the partition, then no problem, you can place that particular process in that partition only. Later we'll see the different algorithms on what basis you select the partition to place the process. That is also one of the most important topic in memory management. How do you place the processes in the different partitions? Which partition will you select for a particular process? So that particular procedure only you have 3 different algorithms: first fit algorithm, best fit and the worst. That I will be explaining you when I teach another example on that particular fixed size and variable. Here in this session I am just telling you the concept of fixed size partitioning and variable size. So this is fixed size partitioning. Now what will happen in case of variable size partitioning? Let us see variable size partitioning now. How are you allocating the processes in variable size? So in case of variable size partitioning, main memory is here, let us assume. So fixed size, earlier what you have seen, that main memory or physical memory is divided into fixed size partitions. Remember the word fixed size, not equal size, fixed size partitions. So here in the variable size, the main memory is not at all divided into partitions. It is simply one particular space, or you call it as, see, Galvin used the word as a whole. Whatever is the memory available, it becomes a whole here. And normally any point of time, I have already told you that the very first part of the main memory is always meant for the operating system, so that you can remember. But here while explaining the concept, I am not including that part. I will just concentrate on the processes. So this is a whole here. That means this much amount of memory is available completely for the different processes. Now suppose if process P2 is moved to the main memory, or you have to allocate space to P2, what is that you will be doing? Nothing, no need to divide the partition. Place P2. P2 size is how much? 120 kb. P2 has taken. Then suppose if the another process P4 will come, and P4 will take 80 kb. Another process P1 wants to come here. Okay, P1 is moved to the main memory. P1 will take 250 kb. This way, as and when the processes comes, I'll just end here, as and when the processes comes, it is getting placed here, or the space is allocated to the different processes. So no memory waste is happening here in the very first time. But what will happen, you just see, suppose if the CPU is interested in executing for the process, CPU is trying to execute the instruction 180, that if CPU wants to execute the process P5, and P1 is making a request for the input output, then P1 will be moved, P1 will come out, and P5 will come in this place. Now earlier what has happened, now P1 was taking a complete space of 250 kb. In that space now P5 has come, but P5 size is how much? P5 size is only 180 kb. Then what will happen now at this point of time? 250 minus 180. How much? 250 minus of 180, 70. So this 70 is now the leftover space in this particular situation, so or in this particular process. Now this 70 is here. Initially there was no problem, one after the other, but what has happened is one process is making an input output request, hence it is moved from the main memory, but the other process which the CPU has to execute is moved into the main memory. So when you say that earlier P1 was there, P1 is moved to secondary memory now, and from secondary memory P5 is brought into the main memory. So this is also one of the concept in the main memory. Remember, see, this we call it as swap out, and this is called as swap in. So this is a procedure called as swapping. Swapping is a method of moving a process from the main memory. Swap out means moving it from the main memory to the secondary memory, and swap in is from the secondary memory to the main memory. So this way these two processes got swapped. So this has led to some space, extra space, or we can say the space which cannot be used. So this is called as once again fragmentation. And likewise, if other processes also get moved to the secondary memory, swap in and swap out takes place, then there may be a situation where you are seeing some more fragmentation. It is leading to some more fragmentation. Let us assume that there is one more process which is there in the secondary memory. That process is moved to the main memory. Suppose P6 is there. P6 is having a size of, let us take some 70 KB. Okay. So P4 is swapped out, and in place of P4, P6 has come in. Okay. P6 size is 70. So leftover space is here in this particular partition now, and the leftover space is how much? 10 KB. Here also it has made some leftover space in this partition. Okay. Likewise, if you try to take few more examples wherein you are trying to move or swap in and swap out, each of that swap in and swap out may lead to some fragmentation here. Now this is 10 KB and this is 70 KB. Fine. Now you assume that there is a process in the secondary memory. Let us assume P7. Fine. P7 is also there in the secondary memory. 75 KB. Let us assume the size for the P7 to be 75 KB. Now if P7 wants to get moved to the main memory, or if you have to allocate space to P7 in the main memory, you are not finding a space here which can fit P7. But if you look into the extra, that is the leftover space in these two partitions, one is 70 KB, okay, here, the other one is 10 KB. If you add this to how much you are getting, 80 KB space is there here, okay. Leftover space or remaining space is 80 KB existing. Process P7 has to be allocated in the main memory. But what is the reason for not allocating P7 is, P7 is not having the space in the main memory is not contiguous. Because one fragment is here of 10 KB, another fragment is here of 70 KB, and definitely this is a contiguous method of allocation. You cannot put a part of the process here and another part of the process here. It has to be in contiguous fashion. That's the reason P7 cannot be moved or cannot be accommodated into the main memory. So this type of situation is, or this type of fragmentation wherein you have space but still you are not able to accommodate the process in the main memory, is called as external fragmentation. So external fragmentation may happen in both variable size as well as fixed size partitioning. External fragmentation, enough memory space. Look at this, enough memory space to satisfy a process request, but available space is not contiguous. That is what you have seen here. 10 KB is there, 70 KB is there, totally you have 80 KB. Process requesting is only 75 KB, but still you cannot satisfy the process request, and that is called as external fragmentation. So you have learnt in this particular session the contiguous method of allocating a memory, contiguous method of allocating a process in the main memory. And there are two types, one is the fixed size partitioning and another is the variable size partitioning. And you have seen that how it leads to fragmentations, internal fragmentation and external fragmentation. Available space is 80 kb, process requesting is 75, are not able to accommodate. So here you can say, if at all it is asked what is the value for this external fragmentation, so in this case the value for the external fragmentation is the size of the process. Remember, many times the students make a mistake here, the size of the process which you are not able to allocate in the main memory, okay, you are not able to satisfy that request, becomes the external fragmentation. The leftover space is how much? 10 plus 70, 80 kb. Don't write 80 kb as external fragmentation, whereas the process size should be written as the value for the external fragmentation. I request my audience to please like, share and subscribe to my channel, and hope this session is useful to you all. Thank you. Bye bye. Take care.